crash course. Today we want to continue our discussion about classic neural networks like perceptron and Adaline, and after that we will learn about backpropagation algorithm to train multilayer perceptron neural networks. Okay, so in the last session we've seen that for one-layer neural networks, we had historically two major approach to train those networks. One of them was Adaline, and another is perceptron. In Adaline, or adaptive linear element, the error is just the squared error, so we have y minus z squared, and z is wjxi. So we have like a one-layer neural network in here with a linear activation function, and the error is the squared error. So we could actually show it by w1 to is x1, and also we could include the bias as the input, as we have seen before, as 1 as the input, and we have b, let's say, in here. So the desired output in this neural network is real output, but we know that we want to use it for binary classification. So the output of the network is 0 if z is less than 0, and it is 1 if z is greater than or equal to 0. Okay, so the question is how to learn these weights. In Adaline, we use the gradient descent, which is wt. So for updating the weights, we use the previous weight minus the learning rate times gradient of error. So it means that if we calculate the gradient, it is plus eta yn minus zn times x of n. Okay, so because the gradient of error, if we replace the error with 1 over 2 y minus z squared, then we could easily derive this. Okay, so this is the learning algorithm in Adaline. Just note that these are just one-layer neural networks. Okay, so this is Adaline algorithm to train and adjust the weights. The second thing is perceptron. In perceptron, we have x1, xd in here, and we have w1 for that too, wd for this input, and after that, so we sum all of wi xi's, and then we could include the bias also in here. This could be z in here, and after that we apply a step function as the activation function. So z is sum of wi xi plus bi, and we could put all of the weights in a vector and also include the bias term. So the learning algorithm in perceptron is that the problem is that we want to find a hyperplane that perfectly separates the two groups of points. So let's say we have two groups of points with labels y equal to 1 and -1. So we have some two group of data points, and the goal of perceptron is to find this hyperplane. Okay, so, and as you could see in here, it is not actually a unique hyperplane, so this is also a solution of this problem. Likewise this one. Okay, so the algorithm of perceptron is like this. So let's write it down in here. Perceptron algorithm. So first we should initialize all the weights. So we initialize the W's, then we cycle through training data or training instances to calculate the sign of W transpose Xi. So in fact we calculate the Z in here, then we apply this sign function or a step function in here, and in fact instead of step function we could use the sign function, which is +1 or -1, because our categories are 1 and -1 in here. So we could use the sign function in here. So we calculate the output of the network, and if this output was not equal to the target label, then we update the weights to W plus YI XI. In other words, for misclassified training data, we update the weights, but for the training data that are classified correctly already, we don't adjust the weights. Okay, so if the good news is that if the data are linearly separable, then the perceptron algorithm converges to a feasible solution. So if you want to have an intuition about how this algorithm works, it is really simple. So let's say these are the data, and we initialize the W, so we probably have something like this. Let's say we have something like this to the space. This is the initialization of W. So with taking the sign, it means that we assign here, let's say +1, and we assign -1 to this region. So when we cycle through all the training instances, then we will see that this pattern misclassified, and this pattern also is misclassified by the neural network. So the perceptron try to adjust the weight and move the hyperplane in this direction to adjust the weight. So maybe in the next step we have something like this, and in the next iteration we have something like this. Okay, so this is how perceptron works. Okay, so the perceptron and Adeline are the networks that just have one layer. Okay, So the networks without hidden units, so if you remember that in the last session we talked about hidden layers. So for example, in here we have one hidden layer, okay? Except the input and the output layer, the intermediate layers are hidden layer. So the perceptron and Adaline don't have any hidden layer, okay? So the networks without hidden units are very limited in the input-output mapping they can learn to model. So for example, if the data are not linearly separable, let's say we have the famous XOR problem. In the XOR problem, we have the data like this. If the input is 0, 0, let's say this is x1, x2, let me to write down the data in here. If we have 0, 0, the output is 0, 0, 1, 1, 1, 0, 1, and 1, 1, 0. So in here we have 0, in here we have 0, and in here we have 1 and 1. So if you look at this data, you could not separate those with just one line. So this perceptron does not converge in this case, which is a really simple example and famous example. So this is an XOR problem, okay? But the neural networks with hidden units could classify this kind of patterns that are non-linearly separable, okay? So we need multiple layers with nonlinear hidden units to be able to make the more complicated model decision boundaries, okay? But the question is, so how to train those models, okay? And how to adjust the weights of that kind of models. We want to talk about feed-forward neural networks, or MLPs. Feed-forward neural networks, or MLPs. So MLP means that multi-layer perceptron. Okay, so instead of just one layer of perceptron, then we have multi-layer of perceptron. So the general schematic of this neural network is like this. We have the input layer, so this is the input units. We have a maybe hidden layer, and we have an output layer, okay? And each input unit is connected to all of the next layer units, okay? And so we call this layer input layer because we feed the neural network input from here. In here we have the hidden layer, and this is the output layer. For this network, we call it a two-layer networks. A two-layer network. Typically, we don't count the input layer as the layer of the neural network. So we call this a two-layer neural network, or one hidden layer neural network. Okay, so this is a two-layer neural network. You could have a network with multiple hidden layers. So we could have, let's say this is the input layer, we have hidden layer here and hidden layer here, and then the output layer. So this is a three-layer neural network or 2 hidden layer neural network. And as you could see in here, because we connect each neuron to all of the next layer units, we call this fully connected layers. Okay, because they are connected to all of the next layer units. So let's see simple example how to write the output in these networks. So let's say this is the input layer. We include the 1 in here, so we could include the bias as the weights, and we have XD in here. We have Wij of layer 1 in here, and we have nonlinear activation function of phi in these units. And let's call the output of these units Z1, Wjk of layer 2, and for this layer, for the output layer, let's say we have the activation function of psi and the output of O1 and O2. Okay, so in general we could write the output as follows. So it is, we start from here. So this output is equal to, first we should apply this activation function in here, and it has some inputs. So the inputs are the sum of j from 0 to m, Wjk of layer 2, Zj, right? So these are the inputs of this neuron. Okay, and we could again expand this Zj based on the previous layer inputs. Okay, so we have the sum again, Wjk of layer 2. Instead of Zj, we could replace that with phi of some of these inputs. So we have I from 0 to d of Wij of layer 1 times xi. So in this way we could write the output of the function based on the inputs. And as you could see in here, it could be highly nonlinear mapping from the input to the output. Okay, based on the psi and phi of which are the activation functions of our network. Okay. Now the question is that arise probably is that how could we compare the wide versus deep networks? So in other words, we could have a network that is too wide. It means that we have, let's say these are the inputs, they are fixed. We could have something like this and the output layer. So this is probably a wide network. For deep networks, we could have something like this. And this is the output layer. So this is the deep network. So the question is that which of them is better in general? The point is that deeper networks may require far fewer neurons than shallower networks to express the same function. So if you want to express the same function with these two networks, in here you probably have much less parameters than this one, okay? And in fact, the number of neurons could be exponentially smaller than the wide network, okay? The next thing is that how could we know, and how could we compose complicated decision boundaries by the neural networks, or how the neural networks acts to create the decision boundaries. To have the intuition about them, let's say we want to create this region, this decision boundary with a neural network. To create this decision boundary, you need a neuron to, so each neuron could actually divide the space into two half spaces. So for example, this neuron could create this line in the space to split the space into two different half spaces. So we need 5 neurons to have this line, this one, this one, this one, and this one, okay? And so let's say these are the inputs. It is the 2D input, okay? So we need 5 neurons in here in the hidden layer. Then we need to aggregate all of those, or take the ANDs to define this region. So we need another neuron, the output neuron, to get the AND of all of these regions. So with an MLP with one hidden layer, we could create polyhedron decision boundaries. Okay, in general, we could write that as in this table, maybe this. So in here we have a structure, decision boundaries, and an example in here. Okay, so if we have a single layer network like Adaline or Perceptron, then the decision boundaries are half spaces, and in the space they create something like this as the decision region, right? So they could not be really complicated decision boundaries. If we have a 2-layer MLP, or one hidden layer in other words, then the decision boundaries are polyhedral, okay? So they could create something like this or something like this, okay? And if you have 3 layers neural network, or 2 hidden layer, you could have union of polyhedrals. So you basically have, so as you could see in here, these are the intersection of half spaces, and likewise when you add a layer, now you could have a union of these polyhedrals. So you could have something like this, a very complicated decision boundaries. So in fact, with 3-layer neural network, you could create approximately all of the decision boundaries that you want. Or in other words, MLPs are universal function approximators. Okay. So now let's see the main question. And here the question is how to train these networks. Okay. So we have a set of training data. We have some inputs and the corresponding output. And we want to find the function f that maps the input space to get the output. Okay, so let's call it f of x with parameters w. So this f could be actually a neural network or MLP. So we need a loss function to train the network, and in fact the total loss is actually the loss function over all of the training data. We could take the average. So this is the loss function for all of the training data. The loss function should be differentiable because we want to use gradient descent method. So when we want to take the gradient, we should have a differentiable loss function. And in fact, we want to optimize the network parameters to minimize this error function. And also, instead of threshold activation neurons, so instead of having something like this, we want to have differentiable activation functions like sigmoid or other differentiable activation functions, because we want to make the network differentiable to be able to take the gradient from the function of the neural network. Okay, so let's see some examples of the loss functions. The most common one is actually, as we have seen that a lot, it is in fact the squared error. In fact, it is the Euclidean distance between the this is the ground truth or desired output and the output of the network. Okay, so this is the error function could be, and it is differentiable, so we could calculate the derivative. So it is relatively easy, and so we could write the gradient as O1 minus Y1 to OK minus YK, right? Okay. So this could probably works well for regression. For classification, for example, we have seen that one good choice of loss function cross entropy loss, which is the yn log of the output of the network minus 1 minus yn times log of O. So this is the cross entropy loss. Okay. Okay. And so this is for binary classification, and if we model the output So if the output of the neural network is the O of n, we should use sigmoid as the activation function of that network, because the O should be between 0 and 1. Okay, so we should use an activation function to squash the real valued input to the 0 and 1. So one simple choice could be sigmoid function as the activation function. For multiple class problem, we have seen we could use softmax as the activation function. So in the softmax, we could have the output is like this. So let's say this is output neuron. So we have z in here. Then we take softmax to calculate the output. So in this case, we could interpret these as the probability of class I given the input x, right? Okay. Now we want to talk about backpropagation. So what is backpropagation? It is, in fact, it is a training algorithm that is used to adjust weights for multi-layer networks or MLPs. And it is in fact based on the gradient descent algorithm, and it used the chain rule. So it used gradient descent, and it used the chain rule to efficiently compute the gradients. Okay, so let's say we have the loss function, which we know now is the sum. We don't need to consider 1 over n because it does not actually change the mathematics a lot. So we have some loss on and yn in here, and the O is the output of the network, and y is the ground truth or desired output. So in gradient descent algorithm, we know that for updating the weights, we could initialize all the weights and biases. Then to update the weights of ij of layer k, we could update that way as the current weight minus learning rate times the derivative of the loss function with respect to wij. Okay, so this is a gradient descent algorithm, but the point is that in MLPs or in multilayer perceptron, we don't know how to calculate this term. Okay, so we want to find a way to calculate these terms. This is actually what backpropagation does. Okay, so we need to refresh calculus a little bit. So to review the chain rule, so if we have a nested function, let's say f of g of x, then if you want to calculate the derivative of y with respect to x, then you could write that as partial derivative of f with respect to g times the derivative of g with respect to x, right? So let's say now we have multiple g in here. So we have g1, g2, gn. gm in here, and again we want to calculate dy to dx. So we could write this as partial derivative of f to g1 with respect to g1 times the derivative of g1 to partial derivative of gm times the derivative of gm. Okay, in other words, we could show this with something like this, which is really like a neural network. We see that. So we have y in here, we have some g1 to gm in here, and we have f in here. Okay, so as you could see, now we could write the output as the f of g1, g2, and we could calculate the derivative of the output with respect to the input based on this chain rule. Okay. So let's see a simple example to get how to calculate these numbers. So let's say we have the f of x, y, and z is equal to x plus y times z. So we could actually show this by graph. So we have x in here. We have the addition operation in here. We have y in here, and after that we multiply those z to get the output y. Okay, so let's say we know that x is -2, y is 5, and z is -4, and we want to calculate the partial derivatives. In fact, this is an introduction to calculate the derivatives for the weights. So we know that in a neural networks, these are used in the gradient descent. So we want to calculate these. To calculate this, first we should go forward in this graph. So we know that it is -2, it is 5, it is -4. So first we calculate the output of this node. So we have 3 in here. So after that we have 3 and -4 multiplied together, then we have -12 in here. Okay, let's call it q in here. The q is x plus y. Okay, so we know that q is x plus y, so derivative of q with respect to x is 1, and with respect to y is also 1. Okay, and we know that f, which is the output, is q times z. Okay, so the derivative of f with respect to q is z, and the derivative of f with respect to z is q. Okay, so we could write the derivative of f with respect to y, the derivative of f, q times this one, right? And we know that it is 1. Okay, so, and also this is z, right? So now we have all of these values to calculate this. In other words, let's say we have 1 as the backpropagation gradient in here. Let's say we have 1 in here. After that, we could calculate the derivative, the partial derivative of f with respect to z, which is 3, right? So now we could calculate the derivative of f with respect to q, which is -4, right? Because we have these two relation in here. After calculating this, we could again backpropagate this to calculate these guys. So now we could calculate this is -4, and we have -4 in here because this is 1 and this is 1, so the -4 propagates into these two branches equally, -4 and -4. Okay, so this is a simple example of how in fact the idea of backpropagation works. In other words, if we want to show this, we could assume that we have a node in here is the activation function, this is the output, and this is the backpropagated gradient in here. So let's say this is x. So the derivative of loss function with respect to x is equal to this guy in here times this derivative, and actually it is related to this activation function. Okay, and similarly for y we could write it is this guy times the derivative with respect to y. Okay, so now we have all the things for backpropagation. So in neural network we have a similar thing. For a neuron, let's say we have f in here, output of the neuron is aj of layer L, and we have wij of layer L in here, and zj to show it more clear. So this is the zj of L, wij of L. So this is the input to this neuron, and this is the output. So we could write AL as the activation function applied and CI of layer L, and ZJ sum of wij times AI of previous layer. Okay, so the point is that we want to calculate the partial derivative of loss with respect to wij, because we need that in gradient descent. So we could write this as partial derivative with respect to aj, L is in here, times the derivative of activation function for the input of that, times AI of previous layer. Okay, so, and we call it sometimes sensitivity and show it with delta J of layer L. Okay, so for backpropagation, we just need to one time feed forward the network and calculate all of the outputs of the neurons to calculate ZJ and AIs. Then we could backpropagate it from the output gradient of the loss function and calculate all of the gradients. Okay, and that's it, and that is backpropagation algorithm. So for backpropagation, first we feed forward the network to calculate all of A and Z for each unit. Then we calculate delta for backward steps. Okay. After that, we update each network weight, as we know that Wij should be the previous weight minus the learning rate times partial derivative of that weight, and we know that how to calculate this. It is delta J times AI of L minus 1 or previous layer times F prime, which is the derivative of the activation function for the input of ZJ. Okay, so this is actually how we could adjust the weights in an MLP or multi-layer perceptron. But don't worry, in Keras and TensorFlow, when you train the network, it automatically handles this for you and train the network. When you just write the train, it trains the network for you automatically using the backpropagation. But we need to have intuition about backpropagation because we will see that it is important to know some disadvantages maybe of neural networks and some deficiencies of neural networks that we want to solve in next sessions. So yeah, that's it for this session. Now you know how to train multi-layer perceptron or MLPs, and hope to see you in the next session. Bye.